Hi everyone, I'm Valentina De Romeri. I'm a researcher at IFIC Valencia, and in this talk I will discuss possible signatures of primordial black hole dark matter at future neutrino experiments DUNE and THEIA. This presentation is based on this paper, which I've done recently in collaboration with Pablo Martinez Mirave and Mariam Tortola. Let me start with a very brief introduction on primordial black hole dark matter. Actually, primordial black holes constitute one of the earliest proposed and appealing dark matter candidates, and they have received renewed interest quite recently after the observation of gravitational waves. Primordial black holes are thought to be formed from the collapse of large inhomogeneities in the early universe before the BBN epoch. And over large cosmological scales, they would behave as particle dark matter, and they would constitute a kind of cold dark matter candidate. Their masses can span over several orders of magnitude, and they have been searched for using different kind of observations and techniques. So currently the parameter space of primordial black hole dark matter is summarized in this plot in terms of this parameter f, which is the dark matter fraction. That means that if f is equal to 1, the totality of the currently observed dark matter in the universe can be made of primordial black holes. And this is given in terms of the primordial black hole mass in solar masses or in grams. As you can see, currently there is one only region which is completely open, which is the so-called asteroid mass region. In the past, there were claims that some constraints from the accretion of primordial black holes in the interior of neutron stars or white dwarfs would apply, or constraints from femtolensing of gamma ray bars. However, eventually these have been proven to be not so robust. So at the moment, this region is fully open. However, we will be interested in the light mass region, which is the one where these evaporation constraints apply, because this is the mass region that we can probe using neutrino experiments. And I will tell you more now about this. If we zoom in on the left-hand side of the previous plot, we would see this other plot where all the constraints that apply in this mass range are shown in more detail. Most of them arise from evaporation. So this means that primordial black holes and in general black holes are thought to evaporate via Hawking radiation, emitting particles near their event horizons. Very light non-rotating primordial black holes with masses below 5 × 10⁻14 grams are expected to have completely evaporated by now. Instead, heavier primordial black holes would have a lifetime longer than the age of the universe, and so they could constitute a good dark matter candidate. Still, they would emit particles via Hawking radiation, so a large number of constraints have been derived on the abundance of light primordial black holes in the mass range between 10⁻15 and 10⁻17 grams from the non-observation of their evaporation products, namely photons, in particular gamma rays, but also electron positrons and neutrinos. Other constraints apply in this region too, from distortions of the CMB or from the heating of neutral hydrogen or the interstellar medium, but I will not discuss these in this talk. So as I was saying, a primordial black hole can emit elementary particles following a black body-like distribution via this Hawking radiation. To compute the spectra of emitted neutrinos from evaporation, we relied on a public tool, which is called Black Hawk, and we took into account two contributions. A primary one, which is from neutrinos directly emitted in the evaporation of primordial black holes, and a secondary one, which instead stems from the hadronization and subsequent decay of primary particles. Moreover, both primordial black holes in the galactic halo and outside will contribute to the differential neutrino flux from primordial black hole evaporation. So concerning the galactic contribution, the differential flux of neutrinos will look like this. Of course, it depends on the dark matter fraction, on the mass of primordial black holes, on this neutrino spectrum emitted in the evaporation, and on this other factor, which is somehow the equivalent of a d factor for decaying dark matter, and it is basically the integral along the line of sight of the dark matter density profile. For the extragalactic contribution, we need to make an assumption, that is that the dark matter is distributed isotropically at sufficiently large scales. Then the extragalactic differential neutrino flux is estimated as the redshifted sum over all epochs of emission. Let's have a look at how the total differential neutrino flux from primordial black holes look like. We assume here a monochromatic primordial black hole mass distribution, and we allow the primordial black holes to rotate, so to have different spin parameters. We are actually here considering a normalized spin parameter, so that the largest possible value is 1. This plot shows the differential flux in terms of the neutrino energy for 3 different primordial black hole masses from 10 to 15 to 10 to 16 grams. The plain lines correspond to a non-rotating primordial black hole. The dashed and long dashed correspond to 2 different values of spin, 0.5 and 0.9 respectively. First of all, we see that if we consider heavier primordial black holes, this leads to reduced fluxes shifted towards smaller neutrino energies. So this somehow tells us that we have an upper limit on the mass of primordial black holes that we can explore using neutrino experiments. Indeed, if we want to investigate primordial black holes with masses above 10 to 16 grams, we will need to observe milder fluxes peaked at energies where sizable backgrounds are present, in particular from solar neutrinos, from geoneutrinos, and from reactor neutrinos, depending on the kind of experiment. Moreover, we see that if the primordial black hole is rapidly rotating with a high spin, some peculiar features appear at high energies. These peaks correspond to the radiation of particles with higher angular momentum, and enhancement occurs when this angular momentum is aligned with the primordial black hole one. The results that I've showed up to now are obtained assuming a monochromatic mass distribution for the primordial black holes. And this is indeed a quite good approximation because it simplifies the calculation and also allows to compare with existing constraints in the literature. However, it is not really realistic because a large variety of formation mechanisms from inflationary models actually predict extended mass distribution for these primordial black holes. So a common approximation that is used is the log normal distribution for the comoving number density, which is given by this expression, where the relevant parameters are the critical mass, which refer to the position of the peak in the power spectrum, and sigma, which is the width of the distribution. So this plot shows how the differential flux is affected if we assume an extending mass distribution versus a monochromatic one, which is depicted with the black curve. So the larger the distribution width, the more the typical peak from the galactic primary contribution is smoothed down, and the flux is still sizable at larger energies. So as I said at the beginning, we were interested in 2 future neutrino experiments, DUNE and THEIA. In particular, first of all, concerning DUNE, this analysis can be performed exploiting the DUNE FAR detector, which will be mainly sensitive to the electron neutrino component of the primordial black hole neutrino flux via its absorption over nuclei of argon. We computed the expected event spectra using the snow globes tool, and we took into account different backgrounds. In principle, solar neutrinos would be a relevant background below 16 MeV, but we got rid of them, cutting the energy range of our analysis exactly there. And then we also have a background from atmospheric neutrinos above 30 MeV. Moreover, even if it has not been observed yet, the diffuse supernova neutrino background would be observable at DUNE, and therefore would constitute the background for this kind of analysis. So we had to simulate it and include it in our analysis. So this plot, the upper panel, shows the expected event spectra at DUNE compared to the expected backgrounds for different values of primordial black hole mass, spin, dark matter fraction, and mass distribution. Then we were also interested in another experiment, which is THEIA, and that is a proposal for a water-based liquid scintillator. Here, the dominant reaction channel would be inverse beta decay. So somehow THEIA would be complementary to DUNE because it would observe the antineutrino component of the flux. Here we have also two additional backgrounds. One is from reactor neutrinos, depending on the location of the experiment. And the other one is from atmospheric neutrinos interacting via neutral currents, which would mimic the inverse beta decay signature. Let's have a look at the expected sensitivities at DUNE. So this plot shows as orange, red, and dark red contours the expected sensitivities. In the left panel corresponds to the assumption of a monochromatic mass distribution, the right one to an extended mass distribution. Also, we show for comparison the current limit set from evaporation using neutrinos, using Super Kamiokande data. This is the the dot dashed contour. We also show for comparison the expected sensitivity at Juno. However, this is 90% confidence level. And also for comparison, we show a combination of all existing constraints on this mass range, mainly from evaporation and from gamma rays, but also other constraints that I showed at the beginning. And these are depicted as the yellow region. As we can see, DUNE would considerably improve the current limit set by Super Kamiokande, and also it is expected to do a bit better than Juno at lighter primordial black hole masses. If we consider a highly rotating primordial black hole and an extended mass distribution, we can also explore higher primordial black hole masses up to 5 times 10 to 16 grams. Concerning THEIA, these are the results. Again, the left panels correspond to a monochromatic mass distribution, the right one to an extended mass distribution. And since THEIA is still a proposal, it is not clear yet where it will be located. So we consider two options. The first one is that THEIA will constitute a fourth module for the DUNE FAR detector. So it will consist of 25 kilotons of volume. And the other option is instead that THEIA would be a separate experiment with a much larger volume of 100 kiloton, whose location is still unknown. So in both cases, THEIA would be able to improve the current bound from Super Kamiokande, and also in this case, the best sensitivities that we get correspond to the cases where we consider primordial black holes which are highly rotating or which have extended mass distributions with large width. So I come here to my conclusions. So primordial black holes are a viable dark matter candidate whose masses can span over several orders of magnitude. Light primordial black holes with masses in the range 10 to 15, 10 to 17 grams would evaporate and produce sizable fluxes of MEV neutrinos via Hawking radiation. So we have explored the possibility of detecting these neutrinos with future neutrino experiments, DUNE and THEIA, and we have shown that both these experiments could considerably improve the existing bound from Super Kamiokande. So the take-home message is that the next generation neutrino facilities could set competitive bounds on the primordial black hole parameter space, which would be complementary to other existing limits from other cosmic messengers, in particular photons. And also, let's keep in mind that even if the quest for primordial black hole dark matter is not one of the main goals of these neutrino experiments, these analyses could be easily included in their physics program, leveraging other existing analyses, in particular for supernova neutrinos. So I thank you all for the attention, for watching this video, and I will meet you in the discussion panel on Monday, 30th of August in the afternoon.